Hello everyone, welcome to Chapter 8. This chapter is dealing with solutions. Here is our chapter outline. In previous chapters we said all matter was either pure substances or mixtures. We're looking at mixtures in this chapter, and mixtures, remember, came in two different types, heterogeneous and homogeneous. When we're looking at a homogeneous mixture, there are two different parts that make up our solution. There is a solvent. This is a component of the solution that's present in a larger amount, is usually doing the dissolving. And then there is a solute. This is a component of the solution present in a smaller amount and is being dissolved. Here's a picture of someone making a solution. The colored crystals would be the solute mixed with the water, which would be the solvent. I'm sure you're familiar with this. If you're a coffee drinker, putting sugar in your coffee would be a very similar experience. Here are some general properties of a solution. They can have two or more components, so it's not limited to the number 2 components. It does have a variable composition. It can be different from location to location. Properties change as a ratio of the solvent to solute to solvent changes. Sorry about that. Dissolved solutes are present as individual particles, and they could come in 3 different types: molecules, atoms, or ions. Solutes remain relatively distributed throughout the entire solution and will not settle out over time, and they can be separated by some very easy physical means such as distillation, decanting, so on and so forth. Here's our first learning check. As always, I encourage you to pause the video, try to read the question and answer it. So in a homogeneous mixture containing 80 milliliters of water and 20 milliliters of alcohol, identify the solvent and the solute. Hopefully after you've read the choices you came up with the answer of B. And there is our answer. Here's another learning check for us. Take a second, pause the video, read each statement and figure out whether you think it is true or false. So on A, a solution may contain more than one solute. That is true. We can get more than one substance to dissolve in a substance. Letter B, all solutions are homogeneous. That is true. Solutions are uniform throughout. That's a definition of homogeneous. Part C, every part of a solution has exactly the same properties as every other part. That is also a true statement. Since solutions are uniform throughout, every part is exactly the same. And the last one, solutions present in a solution will settle out with time, and that is a false statement. It does not separate into parts. Oops. There's our answers. Sorry. Here's another learning check for us. In this case, we have to identify which is the solute and which is a solvent. So in the first one, again, I encourage you to pause the video and try it yourself. But the solute would be the 5 grams, and solvent would be the water. In the second one, it's going to be exactly the same. The one that's present in smaller amount is the solute, and the water will be the solvent. Sometimes water is known as a universal solvent. The third example is going to be the exact same thing, but in this case the water is the solute and the methyl alcohol is the solvent. In the next one they happen to flip them. Okay, so the one that's present in smaller amount, the ethyl alcohol, is the solute, and the solvent would be present in greater amounts. That's the isopropyl alcohol. Hope you can follow my drawings. Section 8.2 deals with solubility. We're going to look at general factors that affect solute solubility, know the meaning of the terms saturated, unsaturated, and supersaturated, dilute, concentrated, aqueous, and non-aqueous when it's being applied to a solution. Solubility is the maximum amount of solute that will dissolve in a given amount of solvent under a certain set of conditions. There are some things that are going to affect solubility. Most solids will become more soluble in water with an increase in temperature. molecules are moving faster, they're bumping into the solute harder, and it's more likely to go into solution. That is not the case with gases. Gases tend to want to increase in size when they're heated, so as you increase the temperature, solubility of a gas will decrease. Here's a chart showing you different solids that are dissolved in different temperatures, and you can see as our temperature goes from 0 to 50 to 100, almost all of our solutes are going to increase in value. Effective pressure on solubility. With solids going into solution, pressure has little to no effect on the solubility. However, when you mess with pressure, it can have a huge solubility of gases in water, and this is what happens with our carbonated beverages. The pressure solubility relationship for gases was first formalized by the English chemist William Henry in 1775 to 1836. This is now known as Henry's Law, and it states that the amount of gas that will dissolve in a liquid at a given temperature is directly proportional to the pressure of the gas above the liquid. In other words, as the pressure of the gas above the liquid increases, the solubility of the gas tends to increase. And the opposite is also true. As the pressure of the gas decreases, the solubility decreases. Here's a picture of a saturated solution. This is a solution that contains a maximum amount of solute that can be dissolved under the certain temperature and pressure conditions. As you can see from the picture, some solute molecules are being dissolved and others might be going back into a solid state. There's a dynamic equilibrium that exists in this bottle to the right. Another type of solution is known as a supersaturated solution. This is an unstable solution that temporarily contains more dissolved solute than that present in a supersaturated solution. This you find in any restaurant or fast food joint with the syrup that they put in the soda and fountain drinks. That's a lot of sugar that they put in there. The most common of encountered solutions fall into the unsaturated solution type. This is a solution that contains less than a maximum amount of solute that can be dissolved under present conditions. The terms concentrated and dilute are also used to convey qualitative information about the degree of saturation in a solution. A concentrated solution is a solution that contains a large amount of solute relative to the amount that you could dissolve, and a dilute solution is a solution that contains a small amount of solute relative to the amount that could be dissolved. Here's a picture showing you a concentrated versus a dilute solution. I'm sure that you can tell that the one on the left is much more concentrated because it's a much darker, deeper blue than the one on the right, and that was filled to a greater volume as well. Another set of solution terms involves the modifiers aqueous and non-aqueous. An aqueous solution is one in which water is the solvent. Non-aqueous solution is a solution in which a substance other than water is the solvent. Here's a multiple choice style question dealing with solubility. As always, please pause the video, read the question, see if you can figure it out. But the question says, what does the temperature and pressure affect the solubility, or how does the pressure and temperature affect the solubility of a gas in water? And hopefully your answer was A. There it is. Here's another learning check for 8.2. For each of the following pairs of solutions, select the solution for which solubility will be the greatest. So we have pressure and temperature conditions, but we got to pay attention to the fact that we are dissolving a gas, and for gases we want to be at the lower temperature possible. So we're looking for the first one here. For B, we're still dealing with the gas. We're messing with pressure this time and keeping temperature the constant. So in this case, carbon dioxide and water would be more soluble at a higher pressure. Now we get to a solid. Table salt is a solid, it's NaCl. And we're going to dissolve it in water, and we're dealing with the same pressure, but different temperatures, and this one seems to be a little bit higher, so we're going to say that table salt will be more soluble in this condition here. And the last one, another solid table sugar in water with a pressure of 2 and temperature of 40 versus a pressure of 1 and temperature of 70. Pressure doesn't do much for solids, so we're looking for the higher temperature condition. More practice with 8.2. We're going to classify each of the following solutions as saturated, unsaturated, or supersaturated based on the following observations. So, as again, pause video, see if you can figure things out. Welcome back, and if you looked at A, agitation, produce a large amount of solid crystals, that would be a supersaturated. Heating the solution causes excess undissolved solute present to dissolve, that would be a saturated. Excess undissolved solute is present at the bottom of the solution container, that would be saturated as well. And the amount of solute undissolved is less than the maximum, that would be our unsaturated. Here's another learning check. Here's a chart of information that you have to look over, and a solution is made by dissolving 34 grams of sodium chloride in 100 grams of water at 0 degrees Celsius. So we would be looking and focusing on this section of our data table, and you're going to tell me whether the solution can be classified as saturated or unsaturated. So sodium chloride happens to be here, so this is the number that we're really going to focus on. And we're not quite up to the 35.7 that it can hold, so this one will be unsaturated because it can still hold more. But then will you classify it as dilute or concentrated? Since it's holding almost as much as possible, we're going to say that it is concentrated. For section 8.3, we're going to look at solution formation. And for a solute to dissolve, there are certain properties that must be overcome. Interparticle attractions, that is. The first one being attraction between the solute particles. That's what's being dissolved. There is a solute to solute interaction. And there's also an attraction between solvent molecules. As they start to dissolve, a new type of interaction arises, and that's the attraction between what's being dissolved and what's doing the dissolving, and that's the solute-solvent interactions. Here are some factors that affect the rate of a solution formation. The first one being the state of subdivision. And a crushed aspirin tablet will dissolve more rapidly than a whole aspirin tablet. The more compact the whole aspirin tablet is, has less surface area, thus fewer solvent molecules can interact with it at any given time. The second being the degree of agitation of the solution preparation. This is stirring the solution. That's going to disperse the solute particles more rapidly and increase the possibilities for solute-solvent interaction. And the third one is the temperature of the solution components. Solution formation occurs more rapidly as the temperature is increased. So at a higher temperature, both solute and solvent molecules move more rapidly. More interactions are likely to occur and more likely to go into solution. Here is our first learning check for 8.3. As always, I encourage you to pause the video, read the question, look at the answers, and see if you can come up with the correct answer. And when you look at the three factors that increase the rate of solution formation, you would find that D is your answer. Here's another learning check. Again, I encourage you to pause the video, see if you can figure out whether the actions will increase or decrease the rate at which dissolving will occur with sugar cube and water. Welcome back. So cooling will definitely decrease our sugar cube mixture. Next up, stirring the solution, that should increase it, because that's agitation. Next up, breaking our sugar cube into smaller chunks, that will increase it, and crushing our sugar to give it a granulated form, that's kind of the same thing as C, so we're going to say it's going to increase. 4 deals with some solubility rules. This is the basis for solubility, and there's a key term down here almost at the bottom that likes, dissolve, and likes. That's usually the good rule of thumb. So in general, it is found that the greater difference in solvent polarity, the less likely they are to become dissolved. So substances of like polarity tend to be more soluble in each other. So likes dissolve and likes. Likes dissolve and likes. That's a key important piece right there. So polar things tend to dissolve in polar solvents. Nonpolar things tend to dissolve in nonpolar solvents. And this is why we need soap in order to get grease and fats off of our hands or clothing when we're washing them. Here's a table for some solubility guidelines for ionic compounds. I would have this handy and ready for test quizzes. We can see most group 1A are going to be able to be dissolved. Same thing is true with ammonia, acetate, and nitrate. There are a few exceptions, and those are denoted right here: silver, lead, mercury. And then with sulfates, you can see the ones that are insoluble as well. Other insoluble compounds, those are listed right here, and some exceptions are over here. So again, have that readily available for any test or quizzes. Here is another handy solubility table. This is playing Battleship, and you just got to pay attention to whether it's soluble or insoluble. Very, very helpful for net ionic equations and just determining whether something is soluble or not. Make a mental note of it, come back to it, and use it if you need to. Here's our first learning check for 8.4. Again, I encourage you to pause the video, read the question, look at the answers, pick the best one. So greater difference in solvent polarity results in, hopefully you were thinking that the answer is B. There's your answer. Here's another learning check. Again, I encourage you to go back and look at the two charts that I gave you, either the just general rules or the one where you have to play Battleship. But figuring out which are generally soluble in water, form compounds with lead, we would be thinking that is C for your answer. Here's another learning check for us. We're going to determine ethanol is a polar solvent, so that means it has a positive and a negative end, and carbon tetrachloride is nonpolar. In which of these two solvents are the following solutes more likely to be soluble? And one that's ionic would go along with the polar. Cooking oil, that's nonpolar, hopefully you would say that is the carbon tetrachloride because likes dissolve in likes. Sugar, that would be polar. And lithium nitrate would also be dissolved in a polar substance. This question is really designed to use the bottom chart here. That's what the book is going to use. So we're going to try to classify these as soluble, soluble with exceptions, insoluble, or insoluble with exceptions. So you just got to find chlorides. Chlorides are right here, and that applies to bromides and iodides. So for A on 21, you're looking for soluble with exceptions. Nitrates are right here, and it doesn't look like there's any exceptions, so they are just soluble. Carbonates are down here. They are insoluble, but with exceptions. Insoluble. I'm not sure if I said that or not. And the last one, phosphates, that's going to be the same exact thing. Last time we used this chart. Let's try using the top chart this time. So we're looking for copper sulfate. So here's sulfate, and we just got to trace it over to copper, which is right here. So that is soluble. right there at copper, so we look up hydroxide, copper hydroxide, plain battleship, it fits right there, so it's insoluble. Copper nitrate, in the same column, we just got to trace it down to nitrate, it's right there, so this one is soluble as well. And copper chloride, another copper compound, it's right here, so it's soluble as well. Hopefully you can get good at using that solubility table or looking at the rules that your book gave you. 8.5 deals with percent concentration units, and hopefully at the end of this you'll be able to calculate solution concentrations in units of percent mass, percent volume, and mass to volume percent. So the percent concentration, again, there are three different ways and I just outlined them: percent mass, percent volume, and mass to volume percent. The first percent concentration is a formula given here, and the percent by mass is as follows: the mass of the solute divided by the mass of the solution times 100. But you got to keep in mind that the solution has two things in it. It has a solute and it has a solvent. Make sure your units are matching 2 on this one. So here is an exercise for us, and just to refresh, our formula was mass of solute over the mass of solution. That's my abbreviation for solution, times 100. So our solute is present in smaller amounts, so the 5.5 would go up on top, divided by the mass of the solution, which remember is the solvent plus the solute, so we have to, and be careful with your parentheses here, 5.5 plus the 78.2 times 100%, and that's how you get the percent mass. When you crunch those numbers, you'll end up getting 6.6 if you round up a little bit. Here's another learning check for us. As always, I encourage you to pause the video and try some of these problems and see if you can get the answers. I will just work them out for you, and hopefully you have tried them on your own. 91.5 is the mass of everything after you add these two things together, and you times it by 100, and you end up getting about 7.1%. Next one, you're going to do 2.31 grams. I should have put the units on the last one. Over 37.2 grams, and your grams will actually drop off times 100, and you'll end up getting about 6.19%. Letter C, you're going to do 12.5 grams divided by the total mass of everything, which is 138 grams times 100, and you end up getting 9.06%. And the very last one, you're going to be 0.0032 grams of NaOH, all divided by 1.2 grams. And this is such a small amount that you could add it on there, but it's not going to change your answer when you do the entire thing. So times 100, you'll end up getting about 0.27%. Work through one of these problems, and hopefully you can follow my process on getting to the other answers. But we're starting with 1.3% is equal to the mass of glucose, which is what we're going to want, mass of X we'll call it, divided by, you got to remember we're dividing by the mass of the solution, so it's 275 grams of water plus X, which is going to be the same up here, times 100. So the first thing I would do is I'd divide by 100 on both sides, and that's going to get you 0.013. We move our decimal over 2 times when we divide by 100, is equal to X all over 275 plus X. Now I want to start trying to get X by itself and off the bottom. So in order to do that, I'm going to multiply both sides by this right here, 275 plus X. And that will cancel it on this side. I'm going to do the same exact thing over here, 275 plus X. And when I distribute this, I think I end up getting 3.575 plus 0.013x is equal to x. Now x's are on opposite sides, so I'm going to subtract 0.013x to get all my x's together, minus 0.013, and 3.575 is equal to, I believe it is, hold on, let me look at my calculator, 0.987x. And then I just got to divide by 0.987, gets my x all by itself. Do the same thing over here, and that's how I'm going to get this answer right there. And that would take too much room for me to do all three of these problems, so it's going to be the same basic process to get this percent, and the answers are provided. There's actually a typo on this slide, so looking at this formula, the percent by volume should be the volume of solute divided by the volume of solution, not solvent. So make sure you're aware of that change. Here's a sample problem dealing with percent concentration. We're going to calculate the volume of the percent of solute 30 milliliters of methyl alcohol in enough water to give us this much solution. So remember, it's your volume of solute over your volume of solution times 100%, and you should end up with this answer right here. Here are some similar problems. Again, I encourage you to pause the video and see if you can calculate what the volume percent is here. So hopefully you tried it, and you would do 20.0 milliliters all divided by 475 milliliters times 100, and you'll get this answer right here. Doing the same thing on the next one, 4.00 milliliters divided by 87.0 milliliters times 100. Again, these drop off, and the answer that you get is right there. The last percent concentration of 8.5 is mass to volume percent, and you can see that you take your mass of solute and divide by your volume of solution, and you multiply it by 100. Here's some practice with the equation that we were just talking about on the previous slide. Again, please pause the video, try this on your own and see if you can get it. But for A, you would do 5.0 grams divided by 250 milliliters, times that by 100, and you end up with this answer here. B is going to be very similar, 85 grams of magnesium chloride over 580 grams, or milliliters, sorry, of solution times 100. Do that and you'll end up with this answer here. Here's the first learning check. So we're looking for a solution that has a mass percent composition that's 10%. So in this one you got to be careful because you want 10%. So the answer would be A in this case, because it's going to be mass of the solute over the mass of the solution, and the solution would be these two things added together, and of course times 100. Here's another learning check for us. As always, please pause the video and try to see if you can figure it out for yourself. But just plugging numbers into the equation, it would be 0.9 times, equals the mass of solute, so that's our unknown, we'll leave that as a question mark or x, all divided by 150 milliliters of your volume times 100, so divide by 100, divide by 100, multiply by 150. And then you'll get your answer. And in this case, the answer was C. We're about halfway done with this chapter. 8.6 deals with molarity. And there's an equation that you should probably put to memory, and that's for calculating the molarity. You just take your moles of solute and divide by your liters of solution. Got to make sure that you're in liters, though. That sometimes catches people. It can't be in milliliters. That brings us to our first learning check for this part of this chapter, and it's just a real quick definition. Hopefully you paused the video and found this to be your answer. Here's an exercise for us to try to use the equation. And in this case, here's our equation. And this has to be in liters. So our moles was given to us. That's 1. We plug that right up on top here. All divided by our volume, but again, it has to be in liters. So we're going to take that decimal, move it over 3 times. And that's how you end up with 8. Okay, notice that they didn't put moles for liter. They call this molar. And a lot of times we'll see that in the lab as concentration of the acid or base that we're using. Here's another sample problem, just trying to get us to use the molarity equation. So I'll write it up here one more time. Volume has to be in liters. So in this case, they give us a 10 molar solution, and they give us 2 moles of sugar, moles, and we have to figure out what is our volume. So in this case, we're going to do a little cross multiplication. Bring your 10 molar down and your volume up, and your volume will be equal to 2.0 moles all over 10 molar, which is really moles over volume, which is in liters. Moles will drop off, liters flips up to the top, and that's how we get this answer right there. Here's another exercise for us. This has one extra step, so we're going to consider separate solutions of NaOH and KCl made by dissolving 100 grams of each in 250 milliliters of solution. We're going to calculate the concentration, which is just a generic way of saying what is the molarity. So remember, molarity is equal to your moles divided by your volume in liters. They didn't give us our moles, so we're going to have to convert 100 grams of NaOH into moles. So you got to determine what the molar mass of Na is off the periodic table. It weighs 23. Oxygen is 16 and hydrogen is 1. Add up all those together and you end up with 40 grams for every 1 mole. Okay, so grams disappear. And when you do 100 divided by 40, you end up with 2.5 moles of NaOH. Now we can use our equation up here at the top. Plug in your 2.5 moles and divide it by 0.250 liters now, and you'll end up with this answer here. You'd have to do a very similar technique with KCl, but KCl, K weighs about 39 off your periodic table, plus chlorine weighs about 35.5. Add up those masses and plug it in right there, and just get rid of this NaOH and put KCl. And then you can divide by this right here, but done very similar way. So just add up your new mass and divide 100 grams by that new mass, and then divide that by 0.25, and you'll get this answer here. Practice, practice, practice. Here's a little bit more practice dealing with molarity. Remember, our equation looks like this. So in this case, they give us 1.4 moles, and our volume is in liters, so we're good there. Just have to divide that, and you get your answer right there. B is done the exact same way, and it looks like the answer is 0.98. C is a little bit different because they give you grams. In order to use this equation, we have to be in moles. So you're going to take your 30.0 grams of HCl. You're going to find your masses off the periodic table. Hydrogen weighs 1, chlorine's about 35.5. Add those together, you end up with 36.5 grams per mole. And then you can divide by the 1.45. So I'll do that real quick. When I do it, I end up with 5.6. I'm hoping that I did that right. I usually do them ahead of time. 5.7 if you round up. Because this turns out to be 0.82 moles, and then you can divide by the 1.45. Oh, actually, I was wrong. My decimal is going to be off. It's going to be 0.56. Get rid of that. 0.57. Sorry about that. This will be done the same exact way. 30 grams of HCl. 1 mole is equal to 36.5 roughly. That's going to give you 0.82 moles again. And then we can divide that by 0.875. And I'll do that real quick. I get 0.94 if we round up a little bit. Eight 8.7 deals with the dilution equation. And I've always seen books write it as molarity times volume. Those are your initial conditions equals molarity times volume. Those are our final conditions. So some books will use a 1 and a 2 for your initial conditions, and these are your final conditions. Using the dilution equation, you should try this problem set. They use concentration, so you can use concentration times your volume equals your concentration times your volume. But these two things are linked. Those could go into those. This is over here. So you divide out your molarity and you end up with 9 milliliters of this 10% solution. And you only want 100 milliliters of solution when you're done. So you need 91 milliliters of water in order to figure that out. Here's another concept check. Again, I encourage you to read the question, look at the choices, see if you can figure out the right one. And in order to do this properly, if you really want to dilute salt water solution, you would just simply add water to your solution. That would decrease your concentration. Here's another exercise dealing with the dilution equation. So again, I'll write it. In this case, what's the minimum volume of this stock solution needed to make 150 milliliters of a 0.800 molar NaOH solution? So these two things are linked. I don't care which side of the equation you put them on as long as they are linked. So I'll put them on this side right here, 0.8 molar times 150 milliliters. And our stock solution is 2 molar times our volume that we're looking for. How much of our volume of our stronger stuff do we need in order to make this weaker stuff? So we'll divide out 2 molar, divide out 2 molar. Hopefully you can see molars will cancel out. We're left with just milliliters. And if you do that math, you'll end up with this answer here. For section 8.8, we're going to focus on the basis of properties and identify a given mixture as a solution, a colloid dispersion, or a suspension. So looking at a colloid dispersion first, that's a homogeneous mixture that contains dispersed particles that are intermediate in size between those of a true solution and those of an ordinary heterogeneous mixture. We can look at a couple things. We can look at dispersed phase and the dispersion medium. When trying to identify a colloid dispersion, we have something known as the Tandel effect. And this is a light scattering phenomena that causes the path of the beam to be visible throughout the colloid dispersion. So when you shine it through a solution, you can't see the path of the light. However, when you shine it through a colloid dispersion, you can see the boundaries of the light, and that will be demonstrated in a picture on the next slide. Hopefully you can see the difference between a solution and a colloid dispersion. Obviously the yellow one is our true solution, where our colloid dispersion is the one in red, where you can see the boundaries of the flashlight light going through that solution. If we're talking about a suspension, we're talking about a heterogeneous mixture that contains particles that are heavy enough to settle out over time under the influence of gravity. Here's a nice chart showing us the difference between a solution, a colloid, and a suspension. Really summarizes everything quite nicely. Okay, so I encourage you to look over all the key bullet points there and see if they make sense to you. Here is a learning check for us. So we're trying to identify what a colloid dispersion is. Take a second and read it, see if you can figure it out. Here is our answer. Hopefully you guessed all of these. Section 8.9 deals with colligative properties, and this is a set of properties of a solution that depends on the number of solute particles present in a given quantity of solvent and not their chemical identities. So things that can happen with colligative properties: we can lower the vapor pressure, we can elevate the boiling point, we can depress the freezing point, and we can change the osmotic pressure. So lowering the vapor pressure is something that can be done by adding non-volatile solutes to the solvent, and it's going to lower vapor pressure of the resulting solution below that of the pure solvent. If we take a look at the next slide, it does a good job of showing us why that happens. So in our first picture here, we have all these molecules that can jump out into the gaseous phase. In our problem over here, we've added some solute, and we don't have as many particles that have access to jumping out of the liquid phase going into the gaseous phase. So hopefully you can see why that would lower our vapor pressure. If you were a chef, maybe you know that you add salt to your boiling water on the stove so that you can cook your pasta or whatever at a higher temperature. So adding non-volatile solute to a solvent raises our boiling point. The reason that we salt our roads in the wintertime is so that we can depress our freezing point. By adding salt or a solute, it's going to lower our solvent's freezing point and thus melt the snow on the road. Okay, at obviously very low temperatures, our salt doesn't work very well, but for the most part, it works pretty good for our winters around here. As always, I encourage you to pause the video, read the question, see if you can figure out what the answer is. And the addition of a non-volatile solute to a solvent affects the pressure in the resulting way, and hopefully you said it's going to decrease our vapor pressure. Our last section is 8.10, dealing with osmosis and osmotic pressure. And osmosis is the passage of a solvent through a semi-permeable membrane that's separating two solutions. Usually one's dilute and one's more concentrated. The semi-permeable membrane is just a membrane that allows certain molecules to pass through it and prohibits others from doing so. Here's a picture depicting osmosis in action. So if we look, we have the semi-permeable membrane on the bottom of this graduated cylinder of some type. Okay, the only thing that's allowed to get through this semi-permeable membrane is water, and things always go from high to low concentration. So there's a high concentration of water out here, a low concentration of water inside, and things just go from high to low. That's a natural tendency for everything to do. So eventually the water column will rise and we'll have equal concentrations outside our semipermeable membrane and inside our semipermeable membrane. Here's a better picture of the semipermeable membrane. Notice the water molecules are allowed to flow in both directions. However, a solute is too big, so if it's going to hit there, it's going to bounce back in the other direction. So over the course of time, we'll have more water molecules entering than leaving until we have equal concentrations of solutions on both sides for our semipermeable membrane. So osmotic pressure is the pressure that must be applied to prevent the net flow of solvent through a semipermeable membrane. So notice on this picture they have almost like a piston that's right here, and it's going to prevent the flow of water through that semipermeable membrane, and things won't be able to go from high to low concentrations. So we have something known as osmolarity, which is used to compare osmotic pressure of solutions. And it's a pretty easy equation to use. To figure out the osmolarity, you just take the molarity that we've been dealing with and you multiply it by I, which is the number of particles produced, by the dissociation of one formula unit. By dissociation, I'm talking about something like NaCl. When it breaks down into solution, it becomes Na positive ions plus Cl minus ions. So there would be two pieces that dissociate in this case. That leads us right into this problem, okay, where the osmolarity is just equal to the molarity times our I, and they tell us that our molarity is 3. And on our previous slide we said that this breaks down into two pieces, so times 2, and that's how we get 6, and our units are known as osmol. So in this exercise we're going to calculate the osmolarity. Again, pause the video, try it on your own. That's just equal to molarity times our I. So with Ki dissociating into solution, we end up making potassium ions plus nitrate ions. So there's actually two pieces. So we're going to take our 2 molar times by 2 pieces, and that's how we get 4 osmoles. And if we do this one, doing the same thing, we have our concentration. That's not a problem, but Na plus, and the SO4 is a 2 minus. There are actually 3 pieces. So you would have 2 moles times 3 pieces, and you end up with 6. And our shorthand for our units is known as this right here. So you might remember these terms from biology and dealing with red blood cells, but we can have hypotonic, hypertonic, and isotonic solutions. Hypo means weak, so this is a solution with a lower osmotic pressure than within the cells. Hypertonic sometimes means stronger or more. This is a solution that contains a higher osmotic pressure than within the side of the cell. And isotonic is one that is equal. Iso means the same, so there's equal osmotic pressure within the cell as same with outside the cell. Here's some effects of bathing red blood cells in various types of solutions. So you can see in a hypotonic solution, our red blood cell is going to swell. Pure water is taking in. In a hypertonic solution, water is going to leave the cell, and we're going to have this weird thing happen to our red blood cells, and in an isotonic, they're going to look normal. Here's a nice table just showing you the difference between hypo, hyper, and isotonic solutions. I encourage you to look it over. Pause the video if I go too fast. Here's a multiple choice style question. What is an isotonic solution? Pause the video and see if you come up with Z for your answer. Here's another multiple choice style question. Again, pause the video, read the question, look over all the choices, and see if you can come up with the right answer. This is really just about how osmolarity is calculated. Hopefully you ended up with C for your answer. Here's another question dealing with dilutions. Again, look over the equation, look over the question, look over your answers, and see if you can come up with this answer right here. And our last two questions, again, same kind of thing. Look over the questions, see if you can figure out the answers. And when you do, there you have it. Thanks for tuning in. Have a great one.